I'm going to pick up on talking about what are the challenges in terms of making machine learning models that are big and how do we squeeze them down. I'm going to give you a preview into some of the things that we're going to be looking at into a lot more detail later on. Now, from a model perspective, one of the key things is when we have a machine learning model, it's all about how well you can shrink or compress the model down without losing its ability to fundamentally look for patterns in data. Let me give you a quick sampling of things that we will be getting into a lot more detail later on. So some examples and techniques we'll be talking about are like pruning. Take a look at this model over here, which is a network of neurons with a bunch of connections. When I prune, what I want to do is be able to take some of the connections away. And when I take some of the connections away, the question that is left is the model that I have on the right-hand side, does it have the same accuracy, or does it lose some accuracy, or is it able to maintain that accuracy as the original model? We might be able to remove certain neurons, completely out of this network, and therefore, by further reducing the amount of computation that's actually needed. In doing so, we shrink the size of the network. We also reduce the computational demand of the network, and therefore we can effectively squeeze this into a TinyML device. And this is a very primitive technique that we will actually be using later on to be able to shrink our models down and to deploy them efficiently. Another thing that we can do is to actually play around with the numerical representation, the values that we actually compute on. Because recall, the embedded systems don't have fancy hardware like a floating point unit, and they tend to do very simple sort of arithmetic because they're supposed to be lean and mean as compared to general purpose computing systems. So a technique that we'll be using quite heavily is called quantization. Quantization is basically this notion that you have a floating point value. Remember, 22 divided by 7, that's a floating point value. You take that floating point value, which is a long number of decimal places, after the decimal point, and you quantize it down. Quantization means discretizing the values down into a small subset of values. So here, the end 8 is basically going from negative 128 to 127, which allows us to represent 256 values. Now, because you only have 256 values, you have to shrink the whole range down, which means you might lose some sort of values that would otherwise be represented in a floating point value. Why in the world would I ever want to do that? Well, a floating point 32-bit value takes 4 whole bytes to represent 4 bytes, versus an int 8 value is simply 1 byte, which means that I get a 4x reduction by simply doing the quantization, which is a huge boost in our model size. Now, I have shrunk down our model automatically by 4x. And there's a whole bunch of associated benefits that come along with this from a system implementation point of view that we'll talk about. Talking about compute, the floating point values that I said before, floating point values need dedicated hardware, often to be able to compute efficiently, because floating point decimal arithmetic is actually quite complex. Versus int 8 or just integer arithmetic is much, much simpler. And it's usually found in every single embedded device. So the key lesson here is that we start by thinking about embedded devices. You want to think about how big the networks are, what sort of precisions that we are representing, and the numerical precisions and numerical formats. There are a slew of things that we need to learn. And I'll teach you some of these, the critical ones, especially as we progress through. There are also some advanced techniques that are on the horizon that are quite important to TinyML. For example, things like knowledge distillation. Knowledge distillation is a really nice and fancy buzzword for explaining how a teacher who knows a lot from years of wisdom and has a lot of information is able to distill down the critical information for the student without losing the nugget, given to a particular task. So the benefit is ultimately is that teacher network, might be big and the student network might be small. Later on, we get into how a teacher network actually translates over to a student network and how we can actually use this mechanism to take something that is, a bigger machine learning task, knows how to, and be able to do many different things and shrink it down to a tiny smaller machine learning tasks that actually knows how to do things better and more specifically. Again, this is just a sneak preview of what's coming down later in the course. And there's more from an algorithm and modeling sort of perspective as to what the algorithms look like. But there's also stuff you need to know at the runtime level, which is really fun because that's one of my favorite topics, by the way. So at the runtime level, you need to start thinking about the hardware first. When you have this big, cloud TPU that Google is building, where you want to be able to run many different kinds of machine learning tasks, for instance, you need a framework, a software framework. So typically, people deal with TensorFlow. TensorFlow is a beautiful framework in which you can write machine learning code. Now, if I want to do machine learning on a smaller device, like a smartphone, which has got much smaller computing capability, if you recall from the previous videos, like the A12 processor, for instance, is much smaller. Well, if you do that, you realize that this particular system has much less memory than a big cloud TPU, and would also have much less compute power, right? And it's only focused on making inferences. In other words, the cloud TPU might actually have to learn to detect patterns in the data. And the smartphone is always going to be basically just looking at patterns of data. There's a big difference when you are learning how to do things and when you only execute or do inferencing. Learning something takes a lot of time. For instance, I bet right now you're learning about TinyML, so your brain is exploding with information, and that has to process and has to figure out all these connections that I'm teaching you about. So you would really want to, you already know about it. So when you do inferencing now, once you've learned this thing, you already know about it. So you wouldn't be thinking so hard about it, right? That's the exact same notion here, training versus inferencing. Your smartphone is only looking at interesting patterns, for instance. It's not training, it's just doing inference. So if that's the case, when you don't really necessarily need to use TensorFlow because it's a rather large framework, you'd want to have a smaller, leaner, meaner software framework that is dedicated to just meeting the specific requirements needed in a smartphone. For example, something that takes less memory, something that has less computational requirements, something that only focuses on the patterns of data, quote unquote, for inference. So if I were to put these two systems next to each other head to head, TensorFlow versus TensorFlow Lite, I'm going to start with the ultimate bottom line and work my way upwards, since this is the most important point over here. Who are these frameworks targeted at? For instance, like if you look at TensorFlow versus TensorFlow Lite, what are the two different frameworks and who are they for? TensorFlow is really targeted at the machine learning researcher who's trying to figure out how to actually build the machine learning algorithm. And they're doing a lot of exploration and they are going through a lot of iterations in the training. TensorFlow Lite is actually focused on the application developer who is really interested in using machine learning algorithms that come out of this training and integrating that into applications that provides the end user services to you and me. And because of this, the frameworks have fundamentally different philosophies. For example, TensorFlow has to do distributed compute. It has to use many cloud TPUs, for example, and many GPUs and all at the same time and try to get machine learning to learn patterns that it finds in the data. Well, we are not learning things on a mobile device. We're just exercising what we learn. So we don't need to communicate a whole bunch of different smartphones. That's a simplification in the software stack. The binary size, when you're running things in big data centers with those big processors that are all coupled together, well, you're not really worried about how much memory the software framework is taking. But if you are talking about putting little TensorFlow framework onto a smartphone, you're really concerned about how much memory it's consuming because you don't want it to use up all the space. And once we get into machine learning models itself, we are dealing with, we are training. In other words, we are learning. So same thing on how the topology of the network looks like. Topology is nothing but a fancy buzzword for saying, like, what do your connections look like between your neurons? And in TensorFlow, because we're still learning to find patterns, we're constantly adjusting things, and you need to be flexible. But then again, on TensorFlow Lite, when we already know what the task that I'm going to perform, I don't need any flexibility. All these things, these parameters, they are all set. The critical difference here between TensorFlow and TensorFlow Lite is the difference as to where we are deploying it. So what does a typical pipeline look like? The first time when you're learning the model, if you want to be able to enhance a picture, for example, on your camera, and what you have to do is learn how to enhance that. So you have to find interesting patterns and data and learn how to make that happen. After that, once you have already figured that out, you just want to make it a function call. You just want to call it. And so we have something, we call it a TensorFlow Lite converter that converts a big beefy model into something that's lean and mean. That gives you a file that's called .tf-lite that's nice and thin. And you take that, and then you can deploy this into different kinds of smartphone devices. So this is your general pipeline. You start with a lot of flexibility, and then you shrink things down, and you make them lean and mean, and then you target them for a specific device. This is effectively what we need to enable the next major step, going from big processors over to smartphone processors into the next smallest little thing. The question is, how do we do it? These devices have even less memory when we talk about microcontrollers. They even have less power than we've looked at before, and we are only focused on inference, very much like the smartphone. So for this, we're going to need to look at the software stack, which is a TensorFlow Lite software stack. Specifically, if you're looking at training a pipeline, for instance, or how things happen, you use TensorFlow right at the beginning. Then after that, we go through a conversion, the optimization, deployment, and the usage is all kind of tied down with TensorFlow Lite. And then when you deploy the model, you're typically going to be deploying it on some kind of given known system on a smartphone, iOS, or maybe a Linux kind of platform, of which you then target, a bigger kind of embedded device, or in the case of microcontrollers, you want to deploy it as a TF-Lite engine. And then you can finally start using it to doing tasks. So I'm just showing you a smartphone here as an example, but the general idea is that once you manage to squeeze things out and put them on a device, then you can really start repeatedly using it. For all of that, we'll be focusing on TensorFlow Lite, and we'll walk you through from TensorFlow to TensorFlow Lite, and in fact, what's called TensorFlow Lite Micro, that's at the runtime level. Now, with that said, what I'm trying to wrap up here in the last 4 videos that we looked at in terms of the challenges, including this one, we saw specifically these challenges that we have in terms of the embedded system side, and the hardware and software machine learning side, and how we want to shrink these models to fit on these tiny devices. Over the course of the program, I'm going to promise you that we're going to learn how to resolve these issues. I gave you a very high-level sampling now, but hopefully this sets the stage in your head as to what kind of things we're going to be picking up as we progress through the program. I'll see you soon.